So my talk this evening is on observing planetary nebulae, but first of all, you sort of need to really understand what we're talking about when we mention planetary nebulae. So when we study astronomical objects, we tend to look at their distribution in space, and if they fall within the bands of the Milky Way, then we term them galactic objects. And obviously, if their distribution is across the whole sky, we call them extragalactic objects, which in general means galaxies and variants on that. Now, within the galaxy, we have a number of different kinds of nebulae. So we have emission nebulae, reflection nebulae, and dark nebulae. And in the category of emission nebulae, we've really got three different types, and that will be planetary nebulae, diffuse nebulae, and supernova remnants. Now, diffuse and emission nebulae tend to be found around young, hot, massive stars, so O-type stars, occasionally B and Wolf-Rayet. Now, because they're young, they don't tend to live very long, so only a few millions of years in the cases of the most massive stars. So they don't have much of a chance to leave their areas where they were born. So in this case, they're usually found in areas where there's active star formation going on. And as it said, they're usually found with the radiation from Wolf-Rayet and O stars. Now, what's the difference between those? Well, Wolf-Rayet stars are named after the two French astronomers who discovered the first ones from their spectra. And they tend to be very massive stars, 30 to 40 solar masses, obviously coming towards the end of their lives. And because of their mass, they tend to be unstable. They throw out lots of material, and they're hot enough to excite that material. So on the right here, we have an image of the Crescent Nebula, which is probably one of the brightest of the Wolf-Rayet nebulae, and obviously a common object for astrophotographers to take. The Wolf-Rayet stars in the middle here, and it's illuminating this shell of material. On the left, we see a typical star formation region, in this case M17 in Scutum, sorry. And it again is illuminated by maybe a few, half a dozen perhaps, very bright O-type stars. And the difference here is that they are extremely hot and extremely massive. Supernova remnants, we all know, these are the end of the life of, well, of a massive star, type 2 star, where the star has reached the end of its life. It's formed iron in the core, which no longer produces energy. The atmosphere collapses and bounces back in an explosion. And we see here a couple of typical examples, Simias 147 in Taurus Auriga, and the IC 443, also known as the Jellyfish Nebulae. They also, as a second type, type 1a, which come, it's actually not clear where they come from, but they're either from a single white dwarf or the merger of two white dwarfs. But the main difference here is that the material thrown out from them expands at very high speeds, as it says there, several thousands of kilometers per second. And because they are the remnants of, in most cases, a massive star, there's a lot of material in the ejecta. Now, when we look at planetary nebulae, I'm not sure how this has come up, but you can see all the little red dots are planetary nebulae that we know of, and they fit in the spiral arms and obviously towards the bulge. Our sun is here in the in this diagram, and we don't see many here, of course, because it's blocked by the stars and dust in the Milky Way's bulge. So most of the objects we see are on this side of the galaxy. If we look at them in projection against the plane, we see there is a difference in the height above the plane, and this is caused by the fact that the galactic disk is not just one disk, it's two. There's a thin disk and a thick disk, and our sun currently lies a little below the plane, and therefore any objects close to us can appear out of the plane. So objects such as these ones here are probably closer to us, and we're seeing projection as it goes up. So this again confirms that planetary nebulae tend to lie in the plane of our galaxy and are thus members of our galaxy. Now, one of the things that we have to explain is the vast variety of shapes and sizes of planetary nebulae. Now, we have to remember that when we look at any object in space, we're seeing a 2D projection of a 3D object. And that means that the orientation of the object to us may show a different ideal than what we expected. So here we have the famous Ring Nebula, which sort of 20 years ago maybe would have been thought to be a sphere. But we now know we're actually looking at a column of gas. So it's like one of these nebulae, but we're seeing it absolutely end on. And this studies of its structure show that that is in fact what it is. Now, some of the nebulae are spherical. There's also a vast difference in size. And in this case, size means age. So this is a diagram to scale of a certain number of planetary nebulae. And we can see here the Ring Nebula again. It's relatively young and thus small. And the range from sort of very small protoplanetary nebulae even, and as they age, they tend to expand out along this circle. The helix, of course, is a famous one in the sky at the moment, up to about 4 light years or so. Now, they don't tend to get much bigger than that because the lifetime of a planetary nebula is only 10 to 40,000 years, and that's governed by the lifetime of the central star and the amount of material of ultraviolet light that it puts out to light up the nebula. So what are they? Well, pre-Hubble, we're talking of the Hubble Space Telescope, not Edwin here, it says that we thought that most stars between 0.9 and 6 solar masses become a planetary nebula. And there was a model called the interacting stellar winds, which was the most popular way to explain them. And in this model, we found that towards the end of the life of a solar mass star or slightly greater, it would become a red giant. It would push out a lot of its atmosphere into space, and this would expand relatively slowly at 20 to 30 kilometers per second, perhaps. And eventually the material thrown off would expose the core, and that would produce a very fast wind that flew out and compressed the material that had come off before, and that's what we thought formed a planetary nebula. Now, after Hubble Space Telescope went up there and started taking lots of pictures of planetary nebulae, we found that the shapes and forms were much more complicated than simple interacting stellar winds models would explain. So then it was suggested that single stars, like our sun, could not become a planetary nebula. It needed to be in a binary system or possibly a common envelope system. However, despite our best efforts, only about 25% of central stars of planetary nebulae are seen to be binaries. We find more, but the percentages aren't increasing. So this suggests that although the model might explain some of the more complicated ones, there aren't enough binaries to be there. And when you think that maybe 50% of the stars in our galaxy are associated with another star, so 50% of the stars are in binary or multiple star systems, this is fairly odd. So as always, it seems that there may be more than one way of making a planetary nebula. As it says there, nature obviously doesn't have an issue doing it because there are quite a few around, and the shapes that we see out there may be both mass and binary dependent, and in this case more massive stars may form some of the more exotic forms of planetary nebulae, and lower mass stars may form sort of the kind that we're thinking of. But also, as it says there, possibly substellar, so Jupiter sized companions could disturb the material enough to cape some of the shapes. And the other problem we have is that we think there ought to be, from a theoretical consideration, maybe 25,000 planetary nebulae in the galaxy, but we only know of maybe 3,500. So there's obviously going to be a lot on the other side, but even if we double what we think we know, there's still a vast discrepancy between what we think there should be and what there actually are. So it says in summary, we think now that the endpoints in the life of stars between 1 and 8 solar masses, they don't live very long. I mean, 40 to 60,000 years may be long on human timescales, while on astronomical timescales, it's extremely short. And I remember a joke that was made when I was doing astrophysics that any event that takes less than 1 million years in an astronomical time terms can be counted as instantaneous. So obviously we've changed our views on that, but in the case of planetary nebulae, they don't really seem to last that long, and they expand quite slowly compared to novae and supernovae. So that's what we think we are. So in terms of our discovery of them, how did this occur? Well, planetary nebulae in general are faint enough that you can't see them with the naked eye. Maybe some claims about that you can, but in general it's felt that you need a telescope. So the first person to do a sort of any kind of survey of the sky was the French comet hunter Charles Messier, and his main interest was in finding objects that were not moving but looked fuzzy, so that when he came across them again, he didn't think he'd found another comet. So as it says there, he discovered an object in Vulpecula, and he recorded it on the chart of a comet, and it was later added to his famous catalogue of non-moving fuzzy objects as the number 27. Messier also discovered himself M57, and this has been somewhat of a change up until recently. That was given to Darquillier, but it was Darquillier who described it as appearing as large as Jupiter and resembling a planet which is fading. So Messier went on to include 4 planetary nebulae in his famous catalogue, 27, 57, 76, and 97. But you need to understand that Messier was not doing an all-sky survey. Messier was looking in areas of the sky where comets might appear, or objects that he found on tracks of comets that he was following. And that's what changed with the next observer. So this is M27. Hopefully you're all familiar with that object. Now, the next person on the scene and overlapping with Messier was William Herschel. And this is the 200th anniversary of his death in 1822 this year. So there's been quite a lot of Herschel events on. But William Herschel briefly was a musician, but with an interest in astronomy. He didn't like the telescopes he could buy, so he started making his own, and with one of those he discovered the planet Uranus from Bath, and later on moved to Slough, and then Windsor, Windsor, Eton, and Slough. And he was more of a scientific mind than Messier, and he wanted to understand how the universe was put together. And he did work on double stars, which showed that Newton's laws worked outside the solar system. But his work on nebulae is perhaps what he's best known for. And he put his telescope, which in this case was an 18.7-inch specular metal mirror, focal length of 20 foot. And in those days, telescopes were defined not by their aperture, but by their focal length. So he had a large 20-foot and a small 20-foot, which had a 12-inch mirror. And he basically put this telescope up as a meridian transit. and the telescope would move up and down, and he would note whichever objects, fuzzy objects, which passed through the field of view. Initially, he wrote that down himself, but he quite quickly realized that having a red light in order to write wasn't going to be good. So he got his sister Caroline to sit in the window in this area, and when he found something, he would call out to her what he'd found and a position in respect to a star, and she would dutifully write it down. So one of the first objects that Herschel found was an object that looked like a disk to him, looked like the planet Uranus that he just discovered. And here we see a sort of a modern image of it. And on the left, there is an image drawn by Lord Rosse using the 36-inch at Burr. And it was him. So Lord Rosse had both a 36 and a 72-inch there, and a lot of his stuff was done with the former smaller scope. But it was him that first saw these ANSI coming out the side and nicknamed it the Saturn Nebula. And nowadays we know it as NGC 7009. But this sort of piqued Herschel's interest that there might be more stuff out there than was in Messier's catalogue, at least the variants that he had at the time. So he started his survey, and over 10 years or so observed pretty much every clear night and found something like 2,500 new nebulae, and he was able to resolve a number of Messier's nebulae into stars. And as with most amateur astronomers, got aperture fever and built a much larger, though ultimately unsuccessful, telescope. And he felt that, if he had a large enough aperture, perhaps he could resolve all the nebulae into stars. Now, we had one problem with that, at least initially, and that was the Orion Nebula, because like most amateur astronomers, he enjoyed looking at that, and he thought that he could see changes over time. Now, this is, obviously, given transparency and conditions like that, you would expect to see changes. So it's perhaps surprising that such an experienced astronomer didn't take that as the reason. However, he kept thinking that way, and then later on he found an object that really committed him to the idea that there was something out there that wasn't made of stars. And this was an object that had a star, brightish star, surrounded by a spherical envelope. And he felt that at the time it was believed that all stars were approximately the same brightness, and therefore faintness meant distance. And it would be very difficult for him, therefore, to explain this as a bunch of stars with another much brighter star involved. So to him, this was proof that there was some other kind of ether. He didn't know what it was, but at least he thought that, along with his observations of the Orion Nebula, that there was something else going on. Now, at the time, Laplace's theory of how stars, etc., formed was coming in, where you had a cloud of gas that would condense into a star. So Herschel thought that perhaps he was seeing that in action with this particular star, and he wrote a paper on nebulous stars, properly so called. And in his classification scheme, he came up with a class purely for nebulae that he thought were planetary, and it was Herschel that actually gave them that name. So not all the objects in his class 4 actually turned out to be what we now would regard as planetary nebulae, and some objects in some of the other classes turned out to be planetary nebulae. So it wasn't 100% successful, but Herschel was pretty accurate at getting some of the stuff in there. So the next chap on the scene was Lord Rosse. Now, Lord Rosse is perhaps better known for building the 72-inch at Burr, which was so massive that it couldn't move, at least not a lot. People always say it was purely a meridian tracking telescope, but in fact it was at the end of it has a universal joint, and the telescope could track an object for about an hour as it moved between the two walls. And on the upper right, we have a view of the Owl Nebula, looking like a rather startled thing looking back at the observer. And at the bottom, we have a modern image, and we can see here that Ross, or one of his observers, was quite mistaken. They put a star in each of the eyes, and obviously in the photograph there isn't. The central star is one there, and they didn't draw that at all. But Ross felt that with his much larger telescope, he was able to resolve some of the so-called planetary nebulae into stars. So he said, right, well, there isn't actually anything like an ether out there. It's just how far away they are. And this is another diagram of the 72-inch in action. And you notice now that the observer had to wear a top hat, so the Jacob Rees-Mogg of astronomers. I'm sure that Chris doesn't force top hats when you're observing out in the field. But they drew a lot of objects with this, and the top one is their drawing of M27 and a number of other planetary nebulae that they could see in the background. So Ross sort of tried to persuade everyone that in reality they were just stars. But before we start criticizing these people, this is a set of drawings and images put together from Angelo Secchi, who was an observer at the Vatican with an 11-inch refractor. And you can see here that these are his drawings, and these sort of compare to modern images. So his drawings are fairly accurate representations of what we see today. So it wasn't a question that just by drawing that you were making mistakes. So how you interpreted these was up to the observer and what their connotations were at the time. However, the game was finally concluded by William Huggins, who was looking at an object in Draco, which we now know as NGC 6543, or the Cat's Eye Nebula. And William Huggins was yet another of these people that inherited a business, made a pile of money, was able to sell the business and retire to a house in Tulse Hill in London, which in those days was a day's horse ride from the centre, which is obviously quite amusing when you think it's like maybe 15 minutes by tube or something. But Huggins was looking to do something differently. And he and a friend of his who was professor of chemistry at Imperial College decided that they would try and use the new science of spectroscopy on astronomical objects. Now, again, we have to remember here, this is before photographic plates, so these are all visual spectroscopes. And he found that most of the objects he looked at had a continuous spectrum, i.e. they were made of stars. However, when he looked at NGC 6543, all he saw was some faint lines in the spectroscope. And his initial thought was that the observatory cat had done something, so it was promptly ejected from the observatory, hopefully not through the dome. But later on, he realized that he was looking at something different. Rather than a spectra of a star, he was looking at a gaseous body. And this is pretty much the spectra that he saw. You can see there's not many lines in it, and most of them misinterpreted. But this was the best they could do at the time. And this is a drawing that appeared in Curtis's famous publication in 1918. And this, of course, is the Hubble image of the cat's eye. So by doing this, they showed that there really was a glowing gas in space, and that forever settled the argument. Now, even so, that was 1864. Even by the first part of the last century, people were still struggling to get good spectra because photographic plates were very slow. So at Lick Observatory, they used the 36-inch refractor, but they basically used a direct vision spectroscope. And in that case, you don't have a slit. but the lines of the nebulae all fall and make little images. So here we've got the Eskimo nebulus. We've got 2 little images of it here, and as you go down. Now they were able by this time to identify most of the elements, but they were struggling with the pair up here. And because the first sign of the element helium was in the sun by Lockyer and others, they thought that maybe they discovered a new element that can only be found in nebulae, and so they called it nebulium. However, there was a problem with nebulium, because by the sort of the first part of the last century, they pretty much knew the periodic table, and you can make a guess at an atom's size and structure from its spectra, and there was nothing really in the periodic table in that location that was empty that would give them that those spectral lines. So it wasn't really until 1927 when the physicist Ira Bowen, working in Stanford in the US, showed that the nebulium came not from a new element, but they came from a strange state of the common element oxygen. So in the case of these became known as forbidden lines, because you couldn't create them on the Earth, and in fact you still can't. But in astrophysical cases, i.e. nebulae, they're mostly excited by collision. So an atom is hit by a wandering electron, gets excited, and then eventually decays by emitting a photon of light. Now, normally when this happens, the atom decays in times of a millionth of a second or so, so basically instantaneously. However, there are certain elements and their structures which allow decay times to be the order of a few seconds. Now, what this means is on the Earth, because even in the best vacuum, there's still enough material flying around that in the time that the atom's excited, it will be hit by another electron or another atom, and it will decay by collision as well. So you can only see these things radiating in very low density environments, i.e. nebulae. And they are represented here by the element, and astronomers tend to use this for doubly ionized elements. So O1 would be neutral, 2 would be singly ionized, 3 would be doubly ionized, and then square brackets around it. So this tells you that you're looking at a forbidden line. You can actually also get semi-forbidden lines, and they just have 1 bracket, but they're not really of interest here. So once they understood this, people thought, well, perhaps we can classify gaseous nebulae based on their spectra. And the team at Harvard, who came up with the well-known spectral classification for stars, tried to propose a spectral class for gaseous nebulae based on various combinations of their lines. Luckily, it didn't take off. So really, what are we looking at? So this is, the famous Hubble picture of the Ring Nebula, and although we can't see it here, we can't see the color. This is the central star, sort of bluish, which means it's very hot, and this is the structure around it. There's another picture of the Owl Nebula, again showing it has more detail than Ross found. And this isn't a strange picture of M27, but this is another nebula which looks very close to it, called MWP-1, just to show that there are other forms of nebulae out there. And this is perhaps what we think of more of as a classical nebula. We think this is a sphere. This is the Helix Nebula, one of the closest, if not the closest, planetary nebulae. It's also quite large, so it's about half the size of the full moon. Unfortunately, from the UK, it's quite low in the sky, and you never get the best views of it from here. But I did have a look at it last weekend at the Hall Woodstar party with one of my smaller scopes. So in that case, a 15-inch. but if it's not the closest, it's probably the second or third closest. There are a couple of other very faint objects that may be planetary nebulae which are closer. They form strange and exotic shapes. This is known as the Ant Nebula for obvious reasons. And this is an odd one. This is known as the Spirograph Nebula for those people old enough to remember spirographs, where you sort of moved a little thing around and made interesting patterns. And this is in Lepus, so it's just below Orion, so coming up now. And also it is interesting because one of the few nebulae show a pinkish color to the eye under certain magnifications and conditions. And this one I put in because for Halloween, you could stick this on your door as a ghoul. It is actually a planetary nebula. It's just a planetary nebula that is interacting with the local interstellar medium, and that has sort of changed the shape from a regular one to this ghoul flying through space. And there are several examples of that around. This is Abell 21 in Gemini, also rising now. And this is known as the Diamond Ring. And this again, Abell 39, I think. And again, this is probably a circular planetary. And they have differing shapes. This one, it took a long time for people to understand it was actually a planetary nebula. Originally, it was thought to be a galaxy. Unfortunately, it's in the southern hemisphere in Grus, so this is 5128, and so it has some very odd shapes. This is NGC 246, again up at the moment. It's known as the Skull Nebula for obvious reasons. I often think that astronomers are on drugs for some of the names they come up with stuff, but that's the way it goes. And this is a faint one showing that, again, it has sort of strange patterns on the outside, which tells us that the central star is probably a binary system, and that's the Saturn Nebula. So why would we want, as amateurs, to observe planetary nebulae? So as it says there, there's a wide range of targets suitable for all sizes of telescopes and observing conditions. Some of the few types of astronomical objects that show color visually. And the reasoning behind that is that your eye has two predominant sets of receptors, cones near the center of the eye, which are can see color, but are not very responsive to light, and rods, which are not responsive to color, but are very responsive to light. So in order to see in color, the object has to be brighter than a certain limit to trigger the cones, and some planetary nebulae are some of the few to do that. And as it said there, the invention of the nebula filter in the late 70s, early 80s made them popular targets. Some people will search on their computer to find new ones, and it says their increased light pollution is making it difficult to find other types of objects, in particular galaxies, etc. So here we see a wide variety of telescopes, a small 80mm, a 20-inch, and a 25-inch in the background. This was at Kelling a few years ago. But even with the small telescope, there are, you can see all of Messier's planetary nebulae plus others. So you don't necessarily need a monster telescope, but with a monster telescope, you can start to find very much fainter ones. And here we see another couple of monster telescopes. The one over here, this is my 22-inch, and this is a 24-inch of a colleague. At Kelling, it's a very strange Kelling because it's actually sunny rather than howling winds and gales. So it's still the largest star party in the UK by a very long way, though. So what about nebula filters? Well, they first came in via Del Woods of Daystar, who is better known for making filters for H-alpha observing of the sun, both for amateur use and for professionals. But it was Jack Marling, who that time was working at the Lawrence Livermore Labs and founded a company called Lumicon, that really took the idea and ran with it. And it was him that came up with the early filters, and a bit like we have with tomato sauce is called ketchup because of the brand, narrowband filters are called UHC because that's what Marlin called his ultra high contrast filters. But they revolutionized the observation of all forms of emission nebulae, not just planetary nebulae. And to understand what they were trying to do, this is a very old set of drawings of streetlight spectra. So we have the orange sodium, high pressure, which are slightly pinker ones, and mercury, which was common in the US, but perhaps not so common here. Now, it turns out that if you look at the spectra of a planetary nebula, then you have these very common lines here. And it turns out that these lines are very near the peak sensitivity of your eye, which is obviously going to be useful. However, not always the case. So these are another 3 planetary nebulae from this 1918 publication. And you can see here they have very strong, what we now know as O3 lines. But in these nebulae, the O3 lines are non-existent. So they're not a panacea always. But this diagram is important. So this gray curve is how your eye responds when it's dark adapted in terms of the color perception. So what this means is that the red lines that you see in photographs from hydrogen alpha appear out here, and your eye has, when it's fully dark adapted, has no sensitivity out there at all. And what this means is that when people first started making filters, a lot of them ended up with a red leak because it was slightly cheaper to do it that way. But it didn't really matter in terms of their performance because your eye couldn't see out there anyway. But these are the 2 main lines from oxygen, the forbidden lines, and this is the hydrogen beta line. So you can see you can design a filter which passes just those lines, and that will make a real difference when you're trying to see nebulae. And these would be, again, a couple of diagrams from common filters. You have to remember, though, that these are idealized. There may be a slight variation between a particular example of these filters. But then very recently, Televue came up with a bandmate filter, which is actually made for them by Astronomic. But the difference here was that there was no red leak at all, and it was a much tighter filter. Unfortunately, the price of it has gone up massively in the last year or so, which is rather depressing. So these filters are quite complicated designs. They're not a colored glass filter like you might have for photography, but they're actually an interference filter. And what they have is a set of dielectric materials deposited on a substrate of glass, and they have to be deposited to an accuracy of 1/4 of the wavelength of light. And in a O3 filter, which is one of the line filters, there could be 60 of such layers, and they all have to be accurately plane parallel, etc. So the failure rate is quite high, again, which goes along with their price. But also because they're Fabry-Pérot interference filters, they only work properly if light comes orthogonally, i.e. at right angles through the filter. If the light travels off axis through the filter, or the filter's tilted, then one of 2 things might happen. One is that the contrast may decrease. The second is that the central bandwidth that you're passing may move, which is of course the basis of the H-alpha filters. You tilted them to change the bandwidth so you could follow spectral lines on the sun. And this is an example of a very poor one. So you'd hope that you're going to get high transmission up here. It would be flat through the area of interest, and as here you can see, it barely reaches 90%. If you're lucky, it's all over the shop. So cheap filters can have disadvantages. So what do? Well, they increase the contrast between the background and the object. And as it says there, no light will be, like no filter has 100% transmission. But the best ones are around 96, 97%. And there are times when you want to use, they're not always going to help. So you use an O3 filter when you're using low power, a UHC type filter at medium power. And high power, you may not want to use a filter at all, as by increasing the magnification also tends to increase the contrast. So there are times when you want to use it, times when you don't. The big problem is if you come to me and say, what kind of filter should I buy? And currently, as it says, there's 125 different makes. Most of them are Chinese clones, often rebadged. Optolong, which is a Chinese maker. And they have usual QC issues you have with much Chinese equipment, that if you buy a filter last year and you buy it next year, they may not be the same. They may have different band paths, narrow and broad and narrow. They change with time for a given filter. But luckily, for those of you familiar with the Cloudy Nights forum, in the eyepieces forum, there's a sticky post which gives you a guide to nebula filters, and you can download a spreadsheet and see what filters do what. And that can be useful if you're trying to do it. And also, people came up with strange types of filters to work with planetary nebulae. You might want, why would you want an anti-nebula filter? Well, some people want to use them to see the central star of a planetary nebula, because there's always going to be a glow of nebulosity in the middle, which will overpower a faint star. There were things like variable filters where you as you turned them, the band pass changed. And for complete and utter loonies, there was a helium line filter, which showed different planetary nebula in a different light or a different shape from what you would normally expect to see it. So what do they look like? Well, they come in two types nowadays, mostly a 2-inch for screwing into 2-inch eyepieces, and 1 1/4 for screwing into 1 1/4-inch eyepieces. And that's generally how you use them. You screw them in the back of the eyepiece. That people came up with the idea of filter slides, and this looks like a good idea, but in practice it's a terrible idea, because this might work in California in the high desert mountains, but here with the exposed filter, as you can imagine, it would be covered with dew in no time at all. But on top of that, to make these work, you needed to use a Barlow, because to throw the light further out. So that was a challenge as well. So people came up with variants on that. So this is a filter for a particular kind of telescope, but you can see here it has a little dew heaters around each filter to try and keep it warm, and hence keep the dew off it in such an exposed way. But the other method of using, which people use to find very small ones, is what we call blinking, where you move the filter rapidly between the eye and the eye lens, and looking for an object that doesn't dim, because stars intend to be driven by at least 2 magnitudes, if not more. And if the object doesn't dim, that's probably the planetary nebula. The problem, as it says here, is if you've got cold hands or gloves, you're likely to end up dropping the filter. So it does have downside. People have gone back to the sort of same way that plugins use. You can get things to look at the spectra. So initially, Ed Barker in the Web Society Handbook Volume 2 came up with this idea of an eyepiece and a prism. I really don't understand how he ever got that to work. And certainly nowadays, with the amount of light pollution, it would be quite difficult. Bausch and Lomb did a transmission grating eyepiece years ago. They obviously they haven't been in business for years. You can get transmission grating filters. The Japanese were quite interested into making these little direct vision spectroscopes. You can see an example here. The problem with these was they were designed for Japanese style eyepieces, so 0.965, and they didn't work particularly well with 1¼ ones, and then the Star Analyzer 100 is a grating that you screw into the back of your eyepiece, and it will give you a spectra. As I say, they can use it with a camera or a telescope, and it's used mostly on small and bright stellar planetaries. And this just gives you an example of what a Star Analyzer might do. The top here is a camera, so this is 6543 again. So you can see here it's showing multiple spectral lines. Visually, you're only really going to see the brightest line of the O3 ones and maybe some smaller bits, but it does show that these things do work. Now, the next part of the thing is what kind of eyepieces should you use? And eyepieces in astronomy is almost a religious discussion, which is sort of based on field of view, cost of eyepiece, whether or not it has green and black or what have you. And a lot of people spend a lot of their time trying to justify why the eyepiece they bought is better than an eyepiece somebody else bought that costs more money. And is the extra 10% worth it? And the only person that can make that decision is the observer themselves. You don't often see Teleview owners going on about other eyepieces, but vice versa happens a lot on the forums. But the thing to think about is that if you're using an undriven scope, then having a wide field of view helps, because it means the object stays in the field of view longer, and thus prolongs your enjoyment of looking at the object. If you have a driven scope, then a lot of Americans swear by these Zeiss type things with maximum 50-degree fields of view, but in an undriven scope that would go out of view so quickly it would get quite depressing. So as it says there, in general, planetary nebulae are small, with the exception of the Helix and some of the Abell ones. So they tend to use high power, which means short focal length eyepieces. But if you want to look at a range of nebulae, then having sort of a high power, medium power, low power eyepiece combination is extremely useful, because it means you can look at them at all sorts of different focal lengths. As it says there, because planetary nebulae are so bright, they can take high power when the seeing allows. Now, what you see will depend obviously on your skill levels, but Horwood a few years ago with my friend's 24-inch, we were able to go up to 800 times or more on some planetary nebulae. I mean, the transparency was awful, but the seeing was superb. And we got images that I don't think we'll ever repeat in terms of the quality, that were not far off photographic. However, you also have to be aware of over-magnifying, and this becomes a problem on things like the forums, where you see someone's got a 63mm refractor and they're saying, well, I'm using 300 times on it. Now, you're probably all familiar with the equation that suggests that the maximum magnification is 50 times per inch of aperture, which obviously in that case would be around 150 times or so. And over magnifying tends to be a problem, and this is something that was thought that Percival Lowell did, and what he was actually seeing, rather than detail in Venus and perhaps Mars, was in fact things in his own retina. So you do have to be very careful about that one. And the other thing is in color. So as it says there, people's color responses and gender response tends to change, which means that if somebody looks in and says, oh, I can see it blue-green, the other one goes, no, it's green. That's a subjective opinion. They're seeing color, but you find it very difficult to compare color views. And as it says there, many men are in fact colorblind to a certain degree anyway. So if all that hasn't put you off, then how do you find planetary nebulae? So we've already discussed Messier. So he found 4. In the NGC, which was the New General Catalogue, which was a compilation of the Herschel's work and others at the time, they found 96 in the NGC, all discovered visually. and 36 in the index catalogues, most of which we discover photographically. And then the first person to try and make a catalogue purely of planetary nebulae was Vorontsov-Veliaminov in 1934, and he had 134 in it, which is, pretty much just the NGC and IC ones that were combined together. But the next one, and perhaps the most famous, was one by Perek and Kohoutek, of the infamous COMET fame, and this was the CGPN catalogue in 1967, and they found 1,300 objects that they believed to be planetary nebulae. However, at the time, what a planetary nebula wasn't particularly well known, and there were a couple of famous quotes, one of which was, "A planetary nebula is defined to be a planetary nebula if nobody objects," which isn't tremendously scientific. And worst of all, a planetary nebula is defined to be a planetary nebula if it appears in a catalogue of planetary nebulae, which again doesn't have a lot of scientific rationale. And this was complicated, but for reasons best known to themselves, they included M1, the Crab Nebula, in that catalogue, and even at the time it was known not to be that. But the fact it appeared in the catalogue meant that in a certain number of amateur books, particularly American ones at the time, it was classed as a planetary nebula purely because of that. And then updated one from Strasbourg-ISO, 92, Kohoutek then produced another variant on his catalogue in 2000 with about 1,500, not the same 1,500, I would have to say. And they came up with a PK system for numbering them here. These guys came up with a PNG numbering system, and Kohoutek went back to his PK system. So the names and numbers got quite confusing in that period. And then later on, there were two MASH catalogues, which are nothing to do with Korean war dramas, but were done with the last plates taken with the UK Schmidt, which were hydrogen alpha of the southern Milky Way, and they found 900 on the first pass, and then with a lot of image processing found another 350. And then a northern equivalent was done with the Isaac Newton telescope called the IFAS survey in 2009 and 2014, and they found about another 500, but this was done with the CCD rather than photographic plates. So where is there a definitive list? Well, in terms of whether it's a planetary or not, there's perhaps the HASH database. Unfortunately, that doesn't contain information that's useful to amateurs, like magnitude. But if an object's in there, then it's been checked and spectroscopically confirmed to be a nebula. So as it says there, it makes a problem being software writers, and new planetary nebulae are being found all the time, often by amateurs, as it says there. And the French are particularly good at this for some reason. And to give you an example of that, I don't have this image in here, but I probably ought to. Just recently, Quentin Parker, who runs the HASH database, was looking at the IFAS data, and they thought they saw a planetary nebula in M37, the well-known cluster in Auriga. So they asked an amateur team to have a go at this one, and Peter Goodhue, who's a British amateur but runs a remote observatory in Spain, and a colleague, did 85 hours of integration time on this object and came up with a huge planetary nebula in M37. Now, the thing that makes it interesting is it's one of the very few planetary nebulae that's actually confirmed to live in the nebula, in the cluster, which is a slight problem because M37 is quite a young cluster, and it's unusual that it would have had a star old enough to become a planetary. Anyway, we've already done these two quotes, but classifying them became a problem. Curtis, in the 1918 Lick publication, decided to try one that was based on form, and this is sort of the groups he came up with and where he thought things fitted in. Vorontsov-Veliaminov came up with a classification system that's perhaps still used by one of the best ones for amateurs to use when classifying it, and he could add letters to make a better definition of things, and the professionals have really cut that down into 5 different types: round ones, elliptical ones, bipolar, quadrupolar, which is basically they've got 4 axes, and point symmetric, which basically means we haven't got a clue. Popular lists, well, there's Messier, NGC, the IC, and Sky Catalog 2000, which is a very old publication but had a list of useful planetary nebulae. And the Astronomical League in the United States has a planetary nebula club, the idea being that it's a list of objects that you can go after. We've already been through the catalogs. You can download this one from ESO if you really want. They have a list of all known at the time planetary nebulae. Once you go beyond that, there are a number of lists of objects. So the Abell planetary nebula list was very popular in the 90s, and then the Minkowski PN list is also relatively popular. And there's a site here called clearskies.eu, and he's produced observing guides to both the Abell and the Minkowski planetary nebulae. Finder charts, well, not many people use paper anymore, but you need a fairly large scale. So Sky Atlas 2000, Uranometria, Millennium, perhaps the best of the current generation is the Interstellarum. There are computer star atlases, Megastar Guide, both free now. Sky Tool 4 is planning, and the Sky X, of course, is the old style one. You can get photographic, though most people now will just use the digitized Sky Survey, and the PK, etc. had their own finder charts for the nebulae. You've also got this program called Aladdin, which is now at version 12, which allows you to download and display from all major imaging catalogs. So you could potentially make your own finder charts based on that. The computer starting, well, Megastar 5 is somewhat out of date now, but was recently released as free software. SkyX Carte du Ciel is also free, and Guide 9.1 is free under the GNU license. I put these in there again. I should really change this because it's now released up to 1.1. But these are more for seeing what's up rather than making finder charts, I would suggest. And this is an example of a finder chart from Megastar 5 with a DSS image overlaid. So this is the cluster M46. It has a planetary nebula that's well known, NGC 2438, as a line of sight object projected in front of it. But also there's a much fainter and much more difficult object, Minkowski 118. And this circle is actually the eyepiece field of view. So by using that at the telescope and getting it, you should be able to find that. Now, I would suggest that to find Minkowski 118, you're probably going to require at least a 45 centimeter, not a 50 centimeter telescope, but that's another matter. So charting software hasn't changed much late. So the thing that's really changed is planning software. So we have Sky Tools 4, which is probably the Rolls Royce of them, but also the most expensive. Astro Planner is probably next. Its main thing is it runs natively both on Windows and Macs. Deep Sky Planner 8, Iron Telescope, is a Windows software that you had to pay for, but he stopped developing it and made it freeware with 332. So you have some software you can do planning for free. And this is just an example of what Sky Tools 4 might look like. So the Bowtie Nebula is perhaps better known as NGC 40. So it gives you information on that, what the best rising set times and what it thinks the best eyepiece to use on it. And this would be the field of view it could give. This is one without an overlaid DSS image, but you could do that. Similar to the one we saw before. So this is 2438, Minkowski 18, and another planetary nebula associated in that area known as the Calabash. This is Deep Sky Planner 8. You might say, well, okay, that's much cruder, but it does have a feature that is missing. So it has a column for the emission lines, and this will give you some idea of what the strongest emission line is, and hence what the best filter to use on that object might be. So this is NGC 40, and we can see here that its strongest lines are H alpha. So using an O3 filter on it would be a huge mistake. So that is quite a useful tool. This is AstroPlanner 2.4 from with the AL list in it, but it shows you again a picture of rise and set times, directions to look, etc., etc. So useful information. An Iron Telescope 332 has again some information that others don't have in what it thinks is your chance of seeing it, as well as some built-in images. However, you do need to be careful. So Iron Telescope links into Megastar, which is very useful. However, sometimes it doesn't have good positions. So in this case, I was looking for an object called Sharpless 271, which is a planetary nebula in Aquila. And this is where Iron Telescope thinks it is. And this is the field of view of the eyepiece. And this is where it actually is. So there is, if you just went on that information, you would never see the nebula. It's actually over here. So you do have to be a little careful. And then there's obviously mobile apps. Many people use now. Sky Safari V7 is possibly the best, but there are many others out there to choose from. This is a Sky Safari, and here I put up the AL list. So everywhere there's an interesting planetary, it puts a little circle, and you can go to that if you have a go-to telescope, or at least know what's up. Again, this is Observer Pro, same kind of information. You get picture, rise and set time, and the best months to have a look for it. I mentioned amateur searches, so there are people who spend their time looking at the Deep Sky Survey, and they do discover new nebulae. But also CCD observers are now finding quite a lot of new stuff, and this is because they're starting to look outside the target. So this area here is known as Soap Bubble Nebula. It's not far from NGC 6888, but nobody had seen it. And it was obviously an object whose time had come, because it was independently discovered by 3 groups over a period of about a month. And here it is here. This is one of the amateur images, and this is what happens when you have a 4-meter telescope. So got that, and then some amateurs are finding some really strange stuff. This is one of the discoveries from the French team. They saw it very faintly on one of the DSS images, and again did horrendously long exposures to find it. But this is truly believed to be a planetary nebula. Right, so if I haven't bored you completely witless, here's your reading for later. This is an excellent book, if it's still available, from Cambridge University Press, on what we thought planetary nebulae were and how they worked. These 2 are guides. This is no longer available, but you can find it sometimes on the used market. This was a classic text. It was published by CUP, but they don't do it anymore, but Melbourne University Press do it. You can buy either a PDF or a paper edition. And then these are sort of the newer text. This is the Night Sky Observer's Guide Volume 4, which is on the Milky Way, and therefore obviously covers a lot of planetary nebulae. And here's a very dog-eared copy of Web Society Handbook Volume 2. If you really get into this, then Kent Wallace made this magnum opus of visual observations of planetary nebulae. He sold it via eBay, and there were only about 100 copies made. However, we had a chat with him, and he allowed at the Web Society to reprint it, and he didn't want anything for it. It was just a service to the community. So you can still buy that, but buy it through the Web Society. And this was a guide associated with the Interstellarum Atlas, and has many challenging planetary nebulae in, and drawings and finer charts for those objects. I put these 2 books in. This one I really would never recommend. It's full of errors, but it does have a list of objects in there, and some people find it useful for that. And if you want to know much more details about individual objects, then this series, Annals of the Deep Sky, which is eventually allegedly going to cover all the constellations, but at the moment is only up to volume 8, but it has some planetary nebulae and detailed information about that. So I mentioned the Abel and Minkowski guides from clearskies.eu. Alvin Huey came up with a Abel guide in particular, and that contains his observations, etc. Of these, that you can get through the Web Society or lulu.com. And this again with a list of objects, but just with charts. I'm not going to test you on all that stuff, but if you want to find out what's going on, these are what the French are finding. This is how you look for them, and that's the hash database. You have to register to use it, but I don't think that's a particularly difficult thing to do. This is just an idea of what the planetarinebulae.net looks like, and that's just the information from hash showing what's there. As I said, for amateurs, not terribly useful. There's no magnitude information. You may want to know a bit more about filters, and there's a couple of websites or links that you can look at for those. And I'll just leave you with that quotation from Walter Scott Houston in one of his Deep Sky Wonders columns. And we'll finish with that one, and I'll take any questions if you've got them. Thank you.